Lesson 5.2 Part B, Misleading Graphs. There are a number of ways in which graphs can be distorted, either intentionally or unintentionally, and this is something the reader must be very observant of, because people want to get across their message and they can distort the data with a graph to make it look like their situation's better or their argument is best. So as a reader and a consumer, you must be very careful and be very aware of how the graphs are drawn. Okay, so how can they be done? Well, they can distort by starting either the vertical or horizontal axes at some point other than 0. So if I gave you a graph and it started at 0, that's okay. But if I narrow that graph down and start, let's say I'm going to start the graph here and here, and ignore this part, then your graph will actually look or only take a picture of this quadrant. Okay? Or let's say, for example, I'm going to only take a look up here and ignore everything below that. So your graph would only focus on this part. And we're going to see an example of that. So you can play around with your axes to make your data look different or differently. They can be distorted by using intervals on the scales so they're not evenly spaced. So you can change the x and y values. You can go by 10s or 5s or 20s because sometimes that affects how it looks. And volume is a measure of space. We'll see an example of what that looks like because you can make something look larger by making it three-dimensional. And you can also use percentages that when actual quantities would be more appropriate. So for example, I can say over half for my sample, over half the class likes a certain food. Okay, but they're not going to tell you that they actually only surveyed 2 people and it was 1 out of 2. So it is half, it's 50%, but the reader would really probably appreciate knowing it was only 1 out of 2 people. That is a distortion and a misleading statistic. Alright, so let's take an example of something with volume. How do the numbers of hours of use claimed for the Extra Life battery compared with the number of hours claimed for battery or brand X? Okay, so let's make sure we're understanding here. This is an Extra Life battery, and this is brand X battery. Okay, so if you look at this, how many number of hours of use claimed for the Extra Life battery compared to the number of hours for brand X? So here they say that this does 200 plus hours and this does 100 plus hours. Well, that's basically twice as long. Okay, that's pretty legitimate. That's a much better result. Okay, now if you look at the picture though, they don't quite look, the Extra Life does not look twice as big. It looks quite a bit bigger, and we'll see why. The length, width, and height of the bar for Extra Life battery are each twice as great as the corresponding measure. Okay, now for example, we know that it said twice as long. So if this is the height of brand X, this is the height of Extra Life. You know, if you compare the two, it's twice as long. So that looks good. How do the volumes compare? Well, now that's different, because if I say that this is X units long, and this is X units long, and this is X units long because it's a cube, and we know that the height here is twice as long as the other height, so is the depth, and so is the width. So they're using that twice as much piece of data 3 times here. Not just height, but also in width and length. So brand X has a volume, if you look at volumes, of X cubed. X times X times X. Where Extra Life has a volume of 2X cubed, or 2X times 2X times 2X, which we know when we distribute the power, we get 8X cubed. So in comparison between these two volumes, between these two volumes that this one, if this is 1x cubed, this is 8x cubed, it's 8 times bigger. So they really got bang for their buck here when they used volume to compare the two graphs. So why does the graph give a misleading impression of the comparative lifespan of the two batteries? Because Extra Life has a shape that is 8 times bigger and not actually twice as big like it's supposed to be. So they took advantage and misled you with that graph. Alright, let's use these two graphs. We have workforce, or women in the workforce. So look at our axes. This is a year. This is in millions female workers, 1960 to 1990. Same with the graph on the right, 1960 to 1990. Okay, so we'll notice some differences here in a minute. In the graph at the left, which bar is twice as long as the bar of 1960? Here's 1960. Which bar is twice as big as that? 1980. That looks about right. Twice as big? Pretty good. In the graph at the right, which bar is twice as long as 1960? Okay, which one would be there? Twice as long? 1970. Don't look at the numbers, just look at the bar. Twice as long. This one's a little bit longer than twice as much. This is pretty close. I actually drew my line a little bit too big. Okay. In which year was the number of women employed about twice as great as the number employed in 1960? Now here they're saying which number. So now we want to look at the axes. Alright, so in 1960, it's 2 units high, so 2 million female workers. Which one is 4 million? 1980. Okay, so if you look at the numbers, you get the answer. Oops, sorry. There we go. All right, which graph gives an accurate representation of the data? Well, 1980 shows up twice, so that would be the left one. Okay, because the left one actually shows you accurately the number and the bar being twice as big. Why is the other graph misleading? Well, if you look close enough, there's really only one difference. And that is that this graph starts at 1. So instead of starting at 0, it started at 1. Now, 1960 and 1990 didn't start at 0 either, but we're not going to go back to 0. That's a huge graph with no data. So this is okay that it goes from 1960 to 1990. That's the data that they collected data with. But here, definitely on the y-axis, they should have started at 0. They narrowed it down. And I could even start at 2. If I start at 2, it would look like this. And there would just be this little nub right here which doesn't show you much. And again, that would be misleading. Now, why would someone choose to use the right graph instead of the left? Okay, well, explain why proponents of governmental funding of daycare centers might choose the graph on the right. Now look who wants to prove their point. Funding of daycare centers. They want money for daycare centers. So what's their argument? Well, if you look at the graph on the right, look how much this is growing. A lot. Now, even though this is growing the same amount, when you compare, so we'll look at 1960 and look at 1990. Look how much more it's grown. It looks 3 times as big. We need more money for daycare because more women are working and it's increasing every year. But here, one would say, well, it's only a little bit bigger than twice as much. It's doubling, that's important, but it's not 3 times as much as this one would do. So it would definitely benefit their argument. Now you can do a lot of this with Excel. You can really manipulate things. Now I want to give you an example here that I came across, and that's that a local district had poor test results one year. And the district said 40% of the student body met the state standards. 60% did not. Now that's not a big deal, okay, in terms of, I mean, it is a big deal, but when you represent the data, you can change how that looks pretty easily, and they did. Now, I created an Excel document to show you how they did this, and this is just a little pictograph of what happened. I put the data in, pass 40%, fail 60%. And once my data was in there, I was going to do a graph. I picked a pie chart. Now it's important to understand this. Make sure I got this right here. If I do a typical pie chart, we're looking at something like this. And that's not what I want. Okay, 40% pass, 40% fail. So if I went straight across, that's half. So it looks something like this. 40%. So here's the pass, here's the fail. Now this does not look good because there's more space for failure than passing. Not a good way to represent their data that they want to hide that they did so poorly. So they make it instead three-dimensional. So they pick three-dimensional, which is down here on Excel. Then once it's there, they can pick 3D rotation. So here's the graph right here, three-dimensional, but then I can rotate it so that the passing can rotate to the front, okay, like I did over here. That's the rotation here. And then I can rotate how I'm looking at it. If I'm looking at it top down, but I can rotate it this way to make that gray space right in front. Now how does this matter? Well, if I'm looking at this, I would see mainly gray. So if I walk by, I would say, wow, a lot of the kids passed. Not even realizing that that gray is actually this much space. So a very good indicator of misrepresenting data with a graph. So you want to always look at the numbers. And this happened, and I was with a bunch of math teachers, and we didn't notice it until it just didn't look right, because we knew they scored poorly, but the graphs didn't show it. And until we sat down and looked at the numbers, did we realize that they actually manipulated the picture. It's a very good example of manipulating the data. And this ends Lesson 5.2, Part B.